But none of them are numbered because just do what's going to be on our quiz Friday?
10, 3, 4.
On the top. It was great. We were all kind of in the
Everybody is okay? Big class, huh? Everybody showed up to that.
Everyone's been going like all of us.
So what I wanted to do today is section 11.1. We talked about it a little bit last time, but I'm going to start from the beginning. First of all, your homework from this section is 5, 9, 13, 15, 19, 23 to 51, odd, 73 and 75. This problem in parentheses, these are limit problems. And these are, you have to, in many of them you have to apply the L'Hopital's rule. And all the tricks that you have learned before for limits, the same tricks apply. Okay? But this would be limits of sequences instead of limits of functions defined on intervals. Okay? So first of all, maybe I could go to so remember what is a sequence, right? A sequence is any function where the domain is the set of all positive integers. Okay. So for example, if I define a of n equals to 2n for n larger than or equal to 1, then this is a sequence. So a of 1 would be 2, a of 2 would be 4, a of 3 is a 6, and so on. If I take the function b of n to be n divided by n plus 1, where n is larger or equal to 1, then b of 1 is half, b of 2 is 2/3, b of 3 is 3/4, and so on. Now, usually we use letters f, g, h to denote a function, but when we talk about a sequence, it's more traditional to use lowercase a, b, c. Usually we use x as the input variable, but when you speak about sequences, the more traditional choice is n. Okay? N or m or k. Those are the usual choices. So again, sequence is a function. The domain is the set of positive integers. Notice that I have the function 2n, right? If I write f of x is equal to 2x, right? If I write f of x is equal to 2x, then what's the difference? So if I write the function, let's say f of x is 2x, what's the difference between the function f and the function a of n? What's the difference? Yeah. Dots, yeah. Another big difference here is that the domains are different, right? The domain of f of x is the interval of all real numbers. So the domain of f is an interval on the real number line, where the domain of a is just the positive integers. Okay. Everybody is clear? All right. So let me go back to slideshow again. If a of n is n squared, where n is larger or equal to 1, then a of 1 is 1, a of 2 is 2 squared, which is 4, a of 3 is 3 squared, which is 9, and so on. If I take b of n to be ln of n larger or equal to 1 again, then b of 1 would be ln of 1, which is 0, b of 2 would be ln of 2, b of 3 would be ln of 3, and so on. Everybody understands the definition of a sequence. Okay. So let's look at this example here. Here I have the function a of n to be n minus 2 to the half. Notice that this function a is not defined when n is 1, because when n is 1, you obtain negative 1 to the half, which is not a real number. So, but if you look at the formula for a of n is defined for any n larger or equal to 2. So any integer, for any positive integer larger or equal to 2, a of n is defined, right? Now, let's look at what are the first few values. What are the first few values of a of n? Well, what's the first value? The first value is when I plug in n equals to 2. When I plug in n equals to 2, I get 0. When I plug in n equals to 3, I get 1. You guys can do it in your head. When I plug in n equals to 4, I get root of 2. When I plug in n equals to 5, I get root of 3, and so on, right? Everybody's okay? So these are the first few terms of this function a of n. Now, when I defined a sequence, I said the domain is all positive positive integers. But in this case, the domain is what? In this case, the domain is all positive integers larger or equal to 2. 1 is not included. Should I call this still a sequence? The answer is yes. I should still call it a sequence. In fact, it doesn't matter where you start your sequence, as long as the domain is in one-to-one correspondence with the sequence of positive integers. That's a sequence. Now, it doesn't matter. So whatever a of n is, I can always make the sequence start at 1, for example. So let's say, note that a of n, the sequence a of n starts at 2, right? The domain starts at 2. And I want to start at 1, right? So I want to go back 1 unit and start at 1, right? The question is, can I do that? Can I change the formula so that I have the same sequence of numbers, but I start at 1? So whenever you have, so in this case, what I'm going to do is replace n in the formula of a of n. Replace n by n plus 1. Okay, if I do that, what do I get? If I replace n by n plus 1 in the formula of a of n, I get n minus 1 to the half, which I'm calling that b of n. I'm calling that b of n. Now notice that what are the first few terms of b of n? The terms of b of n are exactly the same as the terms of a of n. However, b of n starts at 1 now, right? B of n starts at 1, n equals to 1, but a of n starts at n equals to 2. Okay? My point is, if I have a sequence that starts at 2, but I want to start at 1, I can always replace n by n plus 1 and change the formula, and I can start at 1. Now, what if I want to start at, let's say, 0? What should I do? You replace n by n plus 2. What if you want to start at 4 instead of 2? If you go forward, you subtract. Suppose in this case, if I want to start at 4, that means I want to go forward by 2 units, right? So in that case, I am going to replace n by n minus 2. Everybody's okay with that? You guys see this? All right. Now, it is traditional when we speak about sequences. What is the meaning of the notation a parenthesis n? It means the value of the function a is evaluated at n. Right? A of 1 means the value of the function at 1. Right? A of 2, value of the function at 2. When you have a sequence, it's more traditional to write a of n as a subscript n. Instead of writing a of n, people would write a subscript n. And then we think of the sequence as a1, a2, a3, a4. So we are listing the values of the function, right? A1 is the value of the function at 1. A2 is the value of the function at 2. A3 is the value of the function at 3, and so on. And because of this, we think of a sequence as an infinite list. Okay? A1 would be called the first term of the sequence. A2 is called the second term of the sequence. An is the nth term. Everybody's okay? So these are some terminologies that we would use when we talk about a sequence. Any questions? Some notations. How do you express a sequence? Well, sometimes we list out first few terms of the sequence and write ... to express a sequence. Sometimes we use the formula for the nth term. An is the nth term. We use a formula for the nth term and write the formula in brackets. Sometimes we know that n could start at 1, 2, 4, right? So sometimes to be more clear, we use the same notation as in this notation, but we also write n is 1 up to infinity to say that n starts at 1 and then it progresses to infinity over the positive integers. Is that making sense? So these are the notations that are used. What goes inside again? For an is the formula for the nth term. A couple of examples. In the first example, I'm using 3 different ways of expressing a sequence. In the first, in this part, notice that I wrote the nth term. The nth term of the sequence is given by n over n plus 1, the general term. That's the formula for the general term. And then we are writing here n goes from 1 up to infinity. The sequence starts at 1. And then instead of using this notation, people might use this notation where they say an is n over n plus 1. Or this notation is also used. You write down first couple of values, and then you write down the general term. Okay, I call it the general. N over n plus 1 is the general term of the sequence, because that's the formula for finding each term. Everybody is okay? Next example is the same idea. I have the sequence. The general term of the sequence is given by negative 1 to the n, multiplied with n plus 1 divided by 3 to the n. Notice that I didn't bother to write whether n starts at 1 or 2 or 3. If I don't say it, just assume that n starts at whatever the beginning number that makes sense. In this case, it makes sense for n starting at 1, right? So I'll take that. It starts at n equals to 1. You might say it also makes sense when n is 0. It also makes sense when n is, in fact, negative 1, right? Am I making sense? But if it doesn't say, just assume that it starts at 1, if that makes sense. Okay? Everybody's okay with that? Okay, what are the first few values of this sequence? When n is 1, do it in your head, please. When n is 1, what do you get? You get negative 2/3, right? When n is 2, just practice in your head what's the value. I mean, I have the values there. 3/9, right? And you see how to compute this formula, right? Okay, notice that the signs are alternating, right? When you have a sequence where the signs are alternating, what is that sequence called? Is that? No. Alternating sequence, right? Alternating sequence. Here's another sequence. In this case, I have the sequence root of n minus 3. In this case, because of the formula, I have to start at 3, right? And the first few values are given here, and then the general term of the sequence is root of n minus 3. Everybody's okay? Now, if I ask you what is the fourth term? What is the fifth term of the sequence? What would you say? Fifth term? 2. But some of you would probably try to say, well, I should plug in 5 here, right? But if you plug in 5 here, you actually get root 2, right? The thing is, if you start at 1, then if you just plug in 5, then it will be the fifth term. But because you're starting at 3, when you plug in 5, you're actually getting the third term, right? You see that? Is that making? If you start the sequence at 1, then if you plug in 5 in the general formula, you get the fifth term. However, because you're starting at 3, now if you plug in 5 in the general formula, you don't get the fifth term. You get the third term. Right? Is that clear to you? All right. But that issue would not make anything tricky. Okay, that issue really doesn't create any problem. Okay, so another sequence, cosine n pi over 6, n going from 0 to infinity, and in this case the first few values are what? When n is 0, you get 1. N is 1, you get cosine 30, which is root 3 over 2. When n is 2, you get cosine 60, which is half, and so on. So basically, you're looking at what? Multiples of pi over 6, right? Looking at the values of cosine at multiples of pi over 6. Any questions on these examples? By the way, I sent you all the slides before I came to the class. Okay, now let's look at the sequence n divided by n plus 1. So an here, the sequence an here is n divided by n plus 1. Now, an, this is a sequence, so it's a function. If it is a function, it has a graph, right? There are two ways of there are two ways of graphically representing a sequence. One is you pick a real number line, and on the real number line you plot each term. So in this case, what is a1? A1 is half, so that's what I plotted here, right? A2 would be 2/3, so that's what I plotted here. So you plot the terms on the real number line. That's one graphical way of presenting a sequence. Okay? Everybody's clear? Now, what is more traditional? What is more traditional graph of a function? More traditional graph of a function is to plot it in the xy plane, where x values are the domain values, y values are the range values, right? So more traditionally, a function is represented this way, right? So when n is 1, the value of the function is half. When n is 2, the value of the function is 2/3, right? So what's the height of the third point here? The height of the third point is 3/4, right? You see that the sequence is increasing because 5/6, is it smaller than 6/7? 5/6, is that smaller than 6/7? Was that? It is, right? 5/6 is smaller than 6/7. So this sequence is increasing. It's like if you have an apple, if you divide it into 6 pieces and take 5 pieces, versus you divide it into 7 pieces and take 6 pieces, right? And the 6/7 would be bigger. Is that making sense? All right, so that's how we graphically present sequences. Now, any questions on the graph? So the graph consists of points, discrete points. Now, if I ask you what's the graph of x divided by x plus 1, where x divided by x plus 1 is a function defined for all x larger than 1. What's the graph in that case? Well, you add all these points in the curve, right? That's the graph of the function x over x plus 1, right? Everybody is okay with that? But the graph of the sequence is just these points here. And I think someone told me at the beginning that that's how the graph looks like for one of the cases. So when we are graphing a sequence in the second way, right? In the previous slide, my second way of presenting a sequence graphically, we plotted these points, right? 1 and the value of the sequence at 1. Right? 1 and the first term was plotted, 2 and the second term was plotted, right? So these are the points that we plotted in the second graph, right? Everybody's okay with that? So in the second graph, we plotted, for example, 1, A1, 2, A2, 3, A3, and so on. So A1, A2, A3, A4, those are the heights of the points, right? Now, from my graph, was it clear? Let me go back to that again. From these two graphs, would you doubt that the terms of the sequence are always smaller than 1? Which is also clear from the definition, right? N over n plus 1, denominator bigger than numerator, so it's always smaller than 1. And notice that from the two graphs, it seems like that the terms, as n gets larger and larger, the terms of the sequence are getting closer and closer to 1. Okay? So in this case, we will say that the limit of this sequence is 1. Now, the limits of sequences are much simpler than the limits of functions. The reason is, not simpler, simple because when we talked about limits of functions in Calc 1, remember limit x goes to 2, x goes to 3, x goes to 2 from the left, 2 from the right, x goes to infinity, x goes to negative infinity, right? But here, when we talk about the limit of a sequence, we only look at one case, when n goes to infinity. When n gets bigger and bigger, what is happening to the sequence? What is happening to the sequence eventually? That's all we care. In this case, it doesn't make sense to say, what's the limit as n goes to 2? You realize that? Because if I want to say that what's the limit of the sequence as n goes to 2, notice that I cannot let n get closer and closer to 2, right? Because I don't have any more points in between, right? Is that making sense? So the only limit that makes sense for a sequence is the limit as n goes to infinity. What happens to the sequence eventually? What happens as n gets larger and larger? Everybody is clear? So in that sense, there is only one type of limit for a sequence. There wouldn't be any. They are not trying to trick you. Yeah, there wouldn't be any. Okay. How do I sort of see that the limit of this sequence n over n plus 1 is 1? I mean, graphically, we have a guess that the limit was 1. But how do I know exactly that the limit of n over n plus 1 is exactly 1? Well, notice that if I look at the difference, so what is n over n plus 1? N over n plus 1, that's the nth term of the sequence, right? So let's subtract the nth term from 1. What do I get? If I subtract the nth term of the sequence from 1, I am getting what? 1 over n plus 1. Now what is happening to the difference as n gets bigger and bigger? As n gets bigger and bigger, the difference is getting smaller. It approaches 0, right? So the gap between 1 and the nth term of the sequence is getting smaller and smaller, right? So that tells you that the limit is 1. Okay. Another way of seeing it is if I look at if I have the function x divided by x plus 1, right? That's a rational function, right? X over x plus 1. That's a rational function. In Calc 1, if I asked you what is the limit of x over x plus 1, what would you say? The limit as x goes to infinity over all real numbers, right? X goes to infinity over the real numbers. Then what is the limit of x over x plus 1? How did you guys do it? Well, how about applying L'Hopital's rule, right? If you apply L'Hopital's rule, do you get 1? The limit of x over x plus 1 as x goes to infinity? I can apply L'Hopital because infinity over infinity, right? Everybody is clear on that. So the limit of x over x plus 1 is 1. Wouldn't that imply that the limit of n over n plus 1 would also be 1? Because what's the difference between x over x plus 1 and n over n plus 1? Well, n goes over the positive integers only, x goes over all the real numbers, but eventually, if x over x plus 1 goes to 1, n over n plus 1 will also go to 1, right? Is that making sense? Okay, so we use this symbol limit as n goes to infinity, n over n plus 1 is 1. So once again, if we say that the limit of an as n goes to infinity is L, it means that the terms of the sequence are getting closer and closer to L as n gets larger and larger. Everybody's okay? Sometimes instead of writing the symbol, the limit of an as n goes to infinity is equal to L, sometimes instead of that I might say an arrow L as n arrow infinity. It means the way I read it is that an approaches L as n approaches infinity. Everybody is clear? An approaches L as n approaches infinity. Now, when the limit of a sequence exists as a number, when the limit of a sequence exists, we call that sequence a convergent sequence. Convergent sequence means the limit of the sequence exists. Okay? Divergent sequence means the limit doesn't exist. Everybody's clear? If the limit doesn't exist, it's not a number, then it's a divergent sequence. If the limit of the sequence exists, then we say that it's a convergent sequence. Everybody is okay with that? Convergent versus divergent. So I usually don't even say the limit as n goes to infinity when I talk about sequences, because there is only one kind of limit anyway. So it is implied that I'm looking at as n goes to infinity. So sometimes I probably wouldn't even say this. Okay, I'll just say the limit of the sequence is L. And I wouldn't bother to say as n goes to infinity, because that's the only kind of limit that we are looking at. Okay. Questions? Now, graphically, when the limit is L, graphically, how may the sequence look like? Well, it may look like this. Notice that the blue line is the horizontal line at height L, and the dots are the dots represent the graph of the sequence. And what happens when the limit of the sequence is L? The gap between the points and the line approaches 0 as you go farther and farther away from the origin. Am I making sense? So that's how the graph of a sequence with limit L may look like. I mean, these are not the only possibilities. I'm saying graphically that something like this may happen. Okay, this is a little bit technical definition of the limit of a sequence. So when you see this definition, don't get scared because it's not going to be a big deal. Okay, but I want to try to explain this definition to you. Remember, I said as n gets larger and larger, the limit, the sequence gets closer and closer to m, right? But that statement is not precise enough, because how close to it? I'm saying as n gets bigger and bigger, the terms of the sequence are getting closer and closer to L, but how close? How close can you make the terms to L? Am I making sense? And the answer is that I can make the nth term. I can make the nth term as close to L as I desire, simply by choosing n large enough. This is what I'm saying. Let's say you give me a very small number epsilon. Okay, you give me a very small number, the smallest number that you can ever think of. Okay, and you give it to me, and you say, can we make the nth term close to L within that error? epsilon. And the answer is yes. Okay, if the limit is L, I could do that. I can make the nth term as close to L as I desire simply by choosing n large enough. Am I making sense? So you give me a small, suppose someone gives me a small number 0.001. And if I know that the limit is L, that means that I can, let's say I have the sequence lying on the floor, and I'm walking on the sequence, and if the limit is L, if you give me 0.001, I can walk long enough, and after some point on, all the terms will be within 0.01 of L. Am I making sense? After some point on, all the terms will be within 0.001 of L. Now say someone else gives me 0.00001. Okay? Then I might have to walk a little bit more further, but still after some point on, all the terms of the sequence will be within 0.0001 of L. Am I making sense? So I can make the terms as close to L as I desire simply by choosing n large enough. So eventually the terms will be within a small number of L. Okay? So that's what this definition is saying. You can read it and see if you understand that. Okay. So again, the technical definition says you give me any epsilon, and I can find a large n. You give me any epsilon you want, I can find a large enough n so that all the terms after the nth term will be within epsilon of L. So this is what all the sequence, all the terms after the capital nth term will be epsilon of L. Or will be within epsilon of L. Again, one more time, okay? You give me an epsilon, I can find a large capital N such that for any term after the capital nth term will be within epsilon of L. Okay, that's what's the meaning of saying that the limit is L. Graphically, what's happening is that suppose you plot the terms on the real number line, and let's say this blue dot is the number L, and that's the limit of the sequence. So what we are saying is that if you give me a very small number epsilon, okay, then I can choose a large value of capital N such that all the terms of the sequence after the capital nth term will be within epsilon of L. Okay, so all the terms after the capital nth term, and an plus 1, an plus 2, an plus 4, all those terms will be within epsilon of L. Am I making sense? Now, if you choose a smaller and smaller epsilon, you might have to pick capital N bigger and bigger. But eventually all the terms will be within epsilon. Everybody's okay with that? Okay. One more explanation of this definition is graphically what is happening is that you have the blue line is the horizontal line at the limit L, and the green lines are horizontal lines at L plus epsilon and L minus epsilon. Epsilon is a very tiny number. Then if you walk on the, let's say you are walking on the points, if you walk on the points, eventually the points will be within these two green lines. That's the meaning of the limit being L. Now, here's a nice fact that will help us compute limits. Remember that a few minutes ago we looked at the function f of x is x over x plus 1, and we also looked at the sequence an is n over n plus 1, right? And we said that the limit as x going to infinity of x over x plus 1 is, what did we say? 1. And the limit as n goes to infinity of n over n plus 1 is 1. Right? What's the difference between the two limits? In the first limit, it's just that the x is going to infinity, but it goes over all the real numbers, right? In the second case, n goes to infinity, but n goes over only the positive integers, right? Am I making sense? That's the only difference, but they have the same limits. So, in fact, anytime you define a function this way, so anytime you have a function f of x, where f of x is defined for all real numbers x larger than or equal to 1, and x is any real number here. So f of x is defined for all real numbers larger than or equal to 1, right? But corresponding to the function f of x, what's the graph of f of x? It's a curve, right? But so I can define a sequence out of this function by saying the nth term of the sequence is f of n, right? So now n is just a positive integer. Okay? So I can define a sequence as an is f of n, right? Anytime I do that, I define a sequence out of a function defined on the interval from 1 to infinity, then the limit of an is the same as the limit of f of x. Is everybody okay? Notice that I didn't say going to infinity or not, but that's implied, because the limit of the sequence, whenever we talk about the limit of the sequence, we are talking about the limit as n goes to infinity. So in both limits, here x goes to infinity, here n goes to infinity. Okay, the limit of an is the same as the limit of f of x as x goes to infinity if the nth term of the sequence is the same as f of n. Is everyone doing okay with that? So graphically, the graph of f of x is a curve, and then on that curve, if you look at the points corresponding to 1, 2, 3, 4, and so on, those points will be the graph of the sequence, right? Is everyone seeing what I'm saying? So let's say that I have 1 right here, and then I have the graph of the function f of x, and then that's the graph of the function f of x. Then what's the graph of the sequence an? Well, it'll be just bunch of points like this, right, on the curve. So the points will be the graph of the sequence an, right? Is that making sense? All right. So in my next slide, that's what I'm trying to say, that if I have a function f of x, and f of x, let's say, is defined for over the interval from 1 to infinity, and I'm defining a sequence an, which is f of n, then the limit of an is the same as the limit of f of x as x goes to infinity. Everybody is okay with what I just said? So graphically, notice that, let's say the limit is L, so I have the horizontal line at L, and the blue what did you call this color? Pink? Okay, pink. So pink color. So let's say the curve is the graph of the function f of x, And the dots here, the dots are the constitute the graph of what? The sequence. And if the limit of f of x is L, right, is it obvious that the limit of the sequence should also be L? Right, because the sequence is just a bunch of dots on the same curve, right? So if the curve gets closer and closer to the horizontal line, the points will also get closer and closer to the horizontal line, right? Is that making sense? Everybody is doing okay with what I just said? Okay. This will be my last slide. Remember the function x. So here, let's say r is a fixed number. So r could be 2. R is a positive fixed number. R could be half. R could be 3/2. It is just any positive constant. And then what's the limit as x goes to infinity of 1 over x to the r? It's got to be 0, right? Because the denominator is getting, what's the limit of the denominator? If I look at 1 over x to the r, what's the limit of the denominator? Infinity, right? So the denominator is getting bigger and bigger without bound. So the ratio 1 over x to the r will approach 0, right? You guys are okay with that? You saw that in calculus, right? What's the limit of what's the limit as x goes to infinity of 1 over x? What's the limit as x goes to infinity of 1 over x to the 3/2? These are all 0, right? Everybody's okay with that? Whenever the limit of the denominator is infinity, the limit of the numerator is fixed number, non-zero number. Whenever the limit of the numerator is fixed, limit of the denominator is infinity, the limit of the ratio is 0. So if I look at the sequence 1 over n to the r, then the limit as n goes to infinity of 1 over n to the r would be what? 0. Again, r has to be a positive constant, right? If r is, say, -1/2, then everything changes, right? Because when r is -1/2, it is actually n to the what? 1 over n to the -1/2 is in fact the same as n to the +1/2, right? In that case, the limit doesn't exist, right? You guys realize that? Okay. Sometimes when you have a sequence, as n gets larger and larger, the values of the sequence gets bigger and bigger. Okay. In that case, we say that the limit is infinity. So as n gets bigger and bigger, the terms of the sequence are also getting bigger and bigger. The nth term is getting bigger and bigger as n gets bigger and bigger. In that case, the limit is set to be infinity. Is that making sense? So when I say the limit of a sequence is infinity, it means that eventually, so you give me a large number, right? You give me a very large number that you can think of. Then I can walk on the sequence long enough that after some point on, all the terms will be bigger than the number you gave me. Okay? So no matter how big of a number you give me, I can always walk far enough so that after some point on, all the terms are bigger than that number. So that's what I'm saying here. That suppose you give me a really big number n, then I can find a large capital N such that every term after the capital Nth term is bigger than n. So every term after the capital Nth term would be bigger than the number capital N. So no matter how big of a number you give me, I can go far enough along the sequence so that after some point on, all the terms are bigger than capital N. Is that making sense? So that's the meaning of saying that the limit is infinity. Now think of this example here, that suppose I define a sequence where I say, let me write it down here. Suppose that I define a sequence in this way, that an is always 1 if n is even, and an is n if n is odd. What's the limit of this sequence? What is the limit of this sequence? Would you say it's infinity, or would you say it's not infinity? The limit for sure is not a number, right? Because as n goes over the odd integers, right, it gets bigger and bigger, right? So the limit doesn't exist. But is it infinity? Why not? Because infinitely many times it has the value 1. So you give me a big number m, no matter how far I walk, right? There is always a number which is smaller than what you gave me, right? Am I making sense? What I said, the limit is infinity if I walk far enough, all the terms are bigger than the number you gave me, right? That's when the limit is infinity. So you're right. In this case, the limit is not even infinity. Okay? And can you understand what would be the definition if I say the limit is negative infinity? The limit is negative infinity. It just means that it's big and negative, right? Okay, we'll see that next time.
So, Friday, the quiz is just...
Quiz is 10.3 and 10.4. Yes. I will talk to you about that tomorrow.
I can, if you have lecture coming up, if you anything, check that out.
Yes. Give me 1 sec. Do you have a pen with you?
Yes. I'll grab it real quick.
Is there any time that I can come and get like some help? I'm having like some problems with
Yes.
3 and 4.
What are you doing at 4?
I have basketball, but like, do you have any time in like the morning tomorrow or after class tomorrow?
Tomorrow I have time at 10:20 till 12.
Okay.
And I also will be here right after our class ends.
So, can I come like 10, 20 to like 11-ish, and then if
Yeah.
I need more help, I'll stop by again after class?
Yeah.
Okay.
Yeah, go ahead. Oh, did you have a question?
I had a couple and I can just follow you back.
Oh, okay. He just needs a signature so I can get rid of him quickly. Okay, so here's I have to write Cal 2 here.
Yeah.
I don't want to break your...
That's a pretty text.
Okay, so here's Cal 2. And what did I give you last time? Yes, okay. So that probably didn't change. Was that after first exam or the
Yeah.
second exam?
That was after first exam.
Okay, what did you have in the second one?
77, so it's definitely B.
77, okay. Any misses?
No.
This is for what? Football or?
Yeah. Awesome. Thank you.
I'm not sure until the 10th reports.
Okay. Let me just close this off here. Oh, you know what? I think I have a meeting at 3.
Okay.
Can you come back at 4 by any chance? Or this bad time? Okay. What questions do you have? Let me see if I can sort of spend like
One is the
5 to
R
10
equals
minutes.
theta one.
Okay. R equals to theta I can explain pretty quickly, okay?
Okay.
So what's happening with R equals to theta?
I understand that it would be like all the points would be like pi over 6, comma pi over 6 and stuff like that, but I don't know how to like...
No, here's what's happening, right? As theta increases, right? Theta goes from 0 to infinity. What is happening to R? Is R increasing?
isn't it just doing the same thing?
It's increasing though, right?
Yeah.
The point is, as theta goes from 0 to infinity, r goes from 0 to infinity. So
Yeah.
when theta is 0, r is 0. You got this point. But then what happens is that as theta goes from, so at pi over 6, it will have a value, right?
Yeah.
And so pi over 4, it will have a value. Pi over 6, it will have a value. Pi over 2, it will have a value, right? So what's happening here is that it's moving like this. So as your polar axis is moving, the r value is increasing.
Okay.
So what's happening that it keeps increasing as you move the polar axis, and then it's like a spiral. It's like ever going spiral. So you just want to say that, just want to draw this, say that it's a spiral, okay?
Is there any way to like?
Make it any better?
Yeah.
No, I mean, the point is, it's an infinite. It's going around and around and around, and it doesn't stop, right?
Okay. So, but if r equals
But
theta.
the point is, though, the r value keeps increasing. So each next point is farther away from the origin.
Okay.
Right? That's the point you want to make. That the points gets farther and farther away from the origin. The points get farther and farther away from the origin. But that is just a spiral. I have a nice animation of one of the spirals that I wanted to show you, but then I didn't get a chance to do that. Let me see if I have the spiral here.